Okay, yeah, thank you, Dario, for this very nice introduction. I hope I can live up to your expectation now. So, yeah, let me briefly introduce Dario already introduced myself. My name is Markus Ahlers. I'm an assistant professor at the Niels Bohr Institute. And so I'm going to give the lecture on multi-messenger astronomy. And I'm also very happy that my postdoc, Johan Ginolini, is also with us today. So Johan promised to monitor the chat and also Slack if you're signing onto Slack for questions, and we can then address these questions in the break or also maybe tomorrow in the next lecture or in the exercises. So if you have any questions, you can of course also send us emails. And here I again show you the Slack workspace that Dario actually created for this school. And we have a special channel which is called hashtag multi-messenger, where you can basically post questions to the exercises. Okay, and this is here also a QR code that gives you this Slack workspace. Now, my plan for this week is as follows. So today and tomorrow, I'm going to talk about cosmic ray transport, and I will start today by a brief introduction, showing you some slides about the history of cosmic rays and recent observations. And then we will, after a short break, talk about cosmic ray transport equations and ways to derive them. Then my plan for Wednesday is to talk about cosmic ray sources and radiative processes. So this will introduce then high energy gamma ray emission related to cosmic ray acceleration. And then Thursday and Friday this week, I'm going to switch over to high energy cosmic neutrinos, which are of course related to cosmic rays and also gamma ray radiation. So on Thursday, I will talk about recent observations with IceCube and what we have learned about these observations. And then I will close the lecture with multi-messenger astronomy, how we can relate these different observations from the universe. And here on the slide, I also list a couple of useful references. So these are previous lecture notes from schools and also review articles that are freely available on the archive. Okay, so let me start by giving you a bit of an overview of cosmic ray observations, also the historical context. So the history of cosmic rays starts already in the 18th century, so a very long time ago. Coulomb in the 18th century observed that if you have a charged electroscope, then this electroscope will discharge over time. And here on the right-hand side, you see an example of such an electroscope. It's probably not one from the 18th century, maybe a more recent one, but the basic principle is the same. You have a bottle, and this bottle is evacuated, and you have a conducting rod, which is attached to a pair of gold leaves. And when you apply charge to the conductor here, then the charge will of course distribute, and the two gold leaves, because they're very light, will be pushed apart by the opposing charges on these leaves. So the distance of the gold leaves is a measure for the total charge which is contained in the system. And if you watch this over time, you see that the gold leaves come closer and closer together. And so this is what Coulomb observed in the 18th century. This effect could be related to the fact that the system is not perfectly insulated. So in the 19th century, Faraday repeated this experiment, and he could also find that he observed a discharge, and this discharge was apparently not related to the insulation of the bottle itself. And then later, Crookes observed that the discharge is actually related to the amount, the pressure of residual gas that you have in the bottle. So the more gas is in the bottle, the more frequent the discharge happened over time. At the end of the 19th century, people were starting to observe the effect of radioactivity, natural radioactivity, Becquerel and Curie. And they also observed that radioactivity is responsible for ionizing radiation. And this could be a potential source why these electroscopes are discharging over time, natural radioactivity in the environment. So this was the state of the art, the hypothesis at that time. And then in the 20th century, about 100 years ago, cosmic ray physics started by Victor Hess. So Victor Hess was also interested in this effect of ionizing radiation. But it was not clear if this is really coming from earthbound sources or from other sources. So one way to test this is actually to take an electroscope, sit in a balloon and go up in the atmosphere. And if this if the discharge of the electroscope is related to ionizing radiation from the Earth itself, you would expect that the discharge rate is going down as you go up in the atmosphere. And this is what Hess actually observed. If you go up to a height of about 1 kilometer above ground, you see that the discharge rate decreases, but then as you go to higher and higher altitudes, you see that the discharge is actually increasing. And this was the discovery of ionizing radiation, which is not terrestrial, but actually extraterrestrial. And this is the type of radiation that was later then called by Millikan cosmic rays. Hess, by the way, received later in 1936 a Nobel Prize for this discovery, together with Anderson, who observed the positron in cosmic rays. So what Hess actually observed at that time was ionizing radiation from cosmic ray showers. Cosmic rays are very energetic particles which are bombarding our atmosphere. And depending on the charge, the cascade that is developed by the cosmic ray can be very extended. So here you see a sketch where you have an initial cosmic ray proton hitting the upper atmosphere, producing a hadronic and mesonic cascade, which is indicated here by the red arrows and particles. But some of these particles, for example, the pions, decay to give long-lived leptons, muons, and these muons can also be observed on ground. And some particles like the pi0 can decay into pairs of gamma rays, pairs of photons. And these photons will then initiate electromagnetic showers, which are indicated here in blue. So there are various components to cosmic ray air showers. There's also a neutrino component, which is not indicated here, but this is also a very important source these days for neutrino measurements, fundamental neutrino measurements. So as I said, Millikan was actually the one who coined the word cosmic rays for this extraterrestrial radiation. And he was apparently also very visible in the media at that time. So this is here a newspaper article from the New York Times in 1932, where the New York Times here reports the clash between Compton and Millikan. I'm not sure what the quarrel was about at that time, but this was very, very visible in the media. As I said, the cosmic ray shower is a source of short-lived particles and also antimatter like positrons. So cosmic ray physics was very early on very tightly connected to the advent of particle physics. I already mentioned Anderson, who discovered the positron produced by cosmic ray interactions in the atmosphere. And this is here a picture from his measurement where you see the track of a positron, bending track of a positron in a cloud chamber. And together with Hess, he received the Nobel Prize for this. Then Anderson was also involved, together with Neddermeyer, in the discovery of the muon produced by cosmic ray showers. And later on, Powell and Occhialini discovered also the charged pion in photographic emulsions. So basically all electromagnetic interacting long-lived charged particles which can reach the ground level in cosmic ray showers were discovered in this way. And I also mentioned Auger, who observed extended cosmic ray showers at very high energies. And his discovery that you can actually observe cosmic rays on ground is also a way to observe these cosmic rays at very, very high energies these days. So the state of the art today in terms of cosmic ray observations are basically coming from 3 different detection methods. At low energies below about 1 tera-electron volt, you can go into space. So here you see the example of the AMS-2 detector, which is on board the International Space Station, sitting here. And we also have satellite missions like the Pamela detector. And these are, of course, very compact detectors. They cannot be that large because it's very expensive to bring something into space. But the advantage of these detectors is that you have a very good measurements of the energy and the momentum and the charge of the particle. So you can really do isotopic studies with these types of experiments. Instead of going into space, you can also go into the upper atmosphere. So you can also measure cosmic rays by balloon-borne experiments. And here on this slide, I show you one example of the CREAM balloon experiment. So what you see here is the payload, which is actually the cosmic ray detector. And this is here on ground. You see the balloon is presently prepared for its ascent into the atmosphere. And of course, as it goes into the atmosphere, the volume of this balloon will expand due to the lower pressure. So typically these type of experiments happen in Antarctica. So you can go to the shore of Antarctica and start your balloon experiment. It will go up into the atmosphere. And then the balloon will basically follow the currents in the upper atmosphere, which is going on a circle around the South Pole. And in principle, this can go on for a very long time. For example, this CREAM-4 run of the experiment was actually running over a period of longer than 1 month. And basically, you can continue the observation for as long as you want. The only danger is that eventually, due to some turbulence, the balloon is going to move out onto the ocean, and this is what you don't want. And at that point, you basically interrupt the experiment, you detach the payload from the balloon, and then it comes down with a parachute, and it's collected then by the experimentalists. And then finally, I already mentioned Auger, who in 1938 observed that very energetic cosmic rays can produce cosmic ray showers that reach ground. And so these secondary particles produced in cosmic ray showers, they can be observed by various techniques. For example, on ground, you can measure charged particles with water Cherenkov tanks. So light-tight water tanks that are looking for Cherenkov light of particles that are traversing the detector. Or you can also use scintillators for that purpose. And you can also look for the development of the shower in the atmosphere itself by so-called air fluorescence detectors. So charged particles in the atmosphere close to the shower core, they will excite nitrogen in the atmosphere. And these nitrogen molecules will de-excite and produce fluorescence light that can be observed on ground. And there's one big experiment located in Argentina, which is called the Auger Observatory, named after Pierre Auger. And this is a very large detector that is using an air surface array of about 3,000 square kilometers. So this is located in Argentina. And it is also observing the fluorescence light in the atmosphere with detectors here that are located at the edge of the error. So these are the centers here of the green stars on the edges. Okay, so this is basically a very brief introduction to experimental techniques. I see there's actually a question in the chat. Okay, so this was something else. Okay. Then, so based on all these experimental techniques, we can then summarize our observation of cosmic rays today. And this is here given on this slide. So cosmic rays are, to a large extent, energetic nuclei, and to a somewhat lower level, leptons like electrons and positrons. And what you observe is cosmic rays span a very wide energy range. So here in this plot, you see a summary of cosmic ray measurements coming from various experiments. It starts here with a kinetic energy of the order of 1 giga-electron volt and extends 10 orders of magnitude, it's 11 orders of magnitude up to 10 to the power 20 electron volts. So these are very insanely large energies, and it's a big mystery what sort of objects are actually producing these cosmic rays. As I said, at lower energies, we have rather good information. So up to energies of the order of tera-electron volt, we have good observations coming from satellite and balloon-borne experiments that can actually measure individual isotopes in the cosmic ray data. At higher energies, we have to switch over to ground-based observation. And you can imagine that if you have a cosmic ray shower, it's very difficult to infer the initial identity of the cosmic ray particle if you are only able to observe secondary particles on ground. So here the cosmic ray data can only be analyzed on a statistical basis based on average shower properties. And based on these properties, you can estimate the individual composition of particles. But what you see here, if you combine all the data from giga-electron volt to 10 to the power 20 electron volt, is that cosmic rays are following a rather featureless power law spectrum. So here the data is organized in a double logarithmic plots, so log in energy and log in flux, and the flux is multiplied here by a factor e to the power 2.7. So this makes the very steeply falling power law flat at the beginning here. So the initial cosmic ray spectrum is close to e to the power minus 2.7. And then we have only very small features in the spectrum, in particular the cosmic ray Ni, which is between PeV and 10 PeV in energy. So this is a softening in the spectrum, which looks like a Ni if you plot it in this way. And this extends to an energy of the order of a few 10 to the power 18 electron volts, where the spectrum recovers, becomes harder again. And this is called the cosmic ray anchor. So you can imagine that this feature here has the shape of a leg. So in terms of composition, you already see here some of the composition in terms of proton, helium, electron, positrons, and also antiprotons. So there's a small contribution of antimatter in cosmic rays. With the space-based experiments and balloon experiments, you can also look for a much wider composition of cosmic rays. And this is shown here on the left-hand side. It's actually looking kind of blurry on my screen. I hope this is not the same for you. Let me try.
It's a bit blurry, actually.
Blurry, yeah? Yeah.
But the other slides are fine. Huh? Just this one is
on my slides. It looks okay. For some reason, this maybe too much information. So what you're supposed to see is here on the left-hand side again, spectra of cosmic rays, and it starts here with hydrogen and then helium, carbon, oxygen, going all the way down to iron. And in order to better display this, all these elements are multiplied by some power here, 10 to the power minus 21, for example, for iron, to separate these spectra on this plot. So a very characteristic feature that you see here is that independent of the chemical composition, so independent of the isotope, you observe spectra which are almost identical. So all these spectra follow the same power law. And so this is indicating that the mechanism that is actually accelerating these cosmic rays to very high energies does not single out specific isotopes in the data. So it has to be a more generic property of cosmic rays, which is important here. If you compare the cosmic ray spectra, the total abundance of cosmic rays derived from these measurements to that of the solar system, you observe the following. This is shown here in the lower right plot. I think we will also post the slides later on, so you don't worry if you cannot see it now. Let me just say here that the composition of galactic cosmic rays follows mostly the composition that is measured in our solar system, which is indicated here in blue, with some exceptions, some notable exceptions. For example, here at low atomic mass number, you have a much higher abundance of lithium, beryllium, and boron in the cosmic ray data compared to the solar system. And also here in the sub-iron, for sub-iron isotopes, you see a higher abundance in galactic cosmic rays compared to the solar system. So this is an effect which can be understood when we are talking about cosmic ray transport in the galaxy later on in the process which is called cosmic ray spallation. So it turns out that lithium, beryllium, and boron in galactic cosmic rays is mostly dominated by secondary production via cosmic ray spallation. So it's spallation from heavier elements that produce this observed flux at Earth. Okay, so this was my very brief introduction into cosmic ray physics and cosmic ray observations. Are there any questions at this point?
I have one question. Yeah. Could you please turn to page 10?
Yeah.
Yeah, I want to know why the data is not continuous. I mean,
okay, that's a good point. Thank you. I forgot to mention that. So what you see here at higher energies, so this is here an energy of the order of 10 to the power 14 electron volts, so 100 tera electron volt. So this is data here collected by ground-based experiment, air shower experiments. And these air shower experiments have a very hard time to distinguish individual nuclear species in cosmic ray showers. For that reason, I show here the so-called all-particle spectrum. So this particle spectrum is basically a superposition of many different elements. Whereas here at lower energies, I've tried to split this up into the dominating component, which is proton and helium. So helium here is divided by 5. So if you multiply this data by a factor of 5 and add it to the proton, you will roughly get to the level of the all-particle spectrum. Yeah? So basically the all-particle spectrum continues like this here towards lower energies. Yeah. Any other question? Okay. Good. Then, so you already noticed here in this plot, I was talking about very high energies of cosmic rays. And I've used terms like electron volt, giga-electron volt, or zeta electron volt, which is 10 to the power 20 electron volt. So before we start our discussion of the transport phenomena of cosmic rays in our galaxy, I would like to start with giving you some preliminaries about the unit system that we are going to use in the following. So let me switch here now to a Blackboard. Let's see how this goes. Okay, I hope you can see this. I mean, basically you see black now, but you are supposed to see black now.
Yeah, indeed, we see black.
Good. Thank you, Johan. So let me, so I would like to start with some preliminaries about the units that we are going to use and conventions. So in the following, we are going to work with natural heaviside Lorentz units. And for those of you who are already from your work as a PhD student familiar with particle physics, these are basically the conventions which are used also quite frequently in particle physics. So we are going to use in the following that Planck's constant h bar, or rather h divided by 2 pi, is equal to the speed of light is equal to 1. And we will also deal with cosmic ray propagation in electromagnetic fields. So we have to deal with basically Maxwell's equation. And so we will use this, that the permittivity epsilon 0 and the permeability mu 0, which are the two quantities that appear in Maxwell's equation, is also equal to 1. So we don't have to worry to carry around these quantities with us all the time. And if necessary, we will also use the fact that K Boltzmann, which is converting temperature to energy, is also equal to 1. Yeah. So so what does this mean now for the following? So first of all, let me quickly write down Maxwell's equations in Heaviside Lorentz units. So in this case, we have Gauss Law. So the divergence of the electric field is given by the density of the electron, and the divergence of the magnetic field is equal to 0. So these are the two Gauss laws. And Ampere's law is going to look as follows. The rotation of the magnetic field is given by the flux J plus the time derivative of the electric field. And then from Faraday's law, we have the rotation of the electric field is given by the negative of the time derivative of the magnetic field. So in Heaviside Lorentz units, we do not have to worry about additional factors of 4 pi that would appear in Maxwell's equations. So that means, for example, that when we are looking for the electromagnetic force of a point charge, then this is simply given as so force is equal to a radial unit vector, and then you have here q1 q2 divided by 4 pi r squared. So and if we are measuring the charge of individual particles, so qi is equal to zi times the elementary charge of the electron, we can rewrite this equation also as a unit vector, and then you have here alpha times z1 z2 divided by r squared. And so in this factor alpha is now the electromagnetic fine structure constant. Alpha is defined as E squared over 4 pi. And you see with this definition, forces become very compact in notation. And the electromagnetic fine structure constant is given by about 1 over 137 in natural units. So with these conventions of Heaviside Lorentz units, we can also write down the Lorentz force for a charged particle. So the Lorentz force will look as follows. Force is given by the charge of the particle times the electric field plus beta cross the magnetic field. So and beta is here defined as the velocity over the speed of light, but since speed of light is equal to 1 in natural units, it doesn't really matter if we are talking about velocity or normalized velocity. So You can also use the notation where you just use the velocity v instead of beta, which is normalized to the speed of light. Okay, so these are some basic notations and conventions that we are going to use in the following when we talk about cosmic ray transport. If you want to convert back into SI units, then it's useful to remember a couple of identities. So first of all, so conversion back to SI units. So first of all, the speed of light is, of course, in natural units 3 times 10 to the power 8 meter per second. And another useful identity to remember is the combination of h bar times c. This is roughly given as 197 times 10 to the power 9 electron volt meter. So in natural units, these two quantities are equal to 1. So that means if I have a quantity which is expressed in natural units, I can add suitable combinations of c and h bar c into the equation to convert into the corresponding length scale in SI units. And yeah, to give you one example, we will also talk about magnetic field strength in the following. So let's talk about the quantity of 1 Tesla. So in SI units, 1 Tesla is simply given as 1 volt second divided by meter squared. So I can rewrite this by inserting a factor of E, the elementary electron charge. So this makes this electron volt times seconds over E times m squared. And now if I use natural units, I can basically add now various combinations of C and h bar c. So this will be electron volt second. From the definition of alpha, E squared over 4 pi, I can write E as square root of 4 pi alpha. Yeah, and this is what I'm going to use here, 4 pi alpha and meter squared. And then I will multiply this equation now by the speed of light and by h bar c. So these two quantities in SE units have now the dimension electron volt meter squared over seconds. And you see that by using this identity, the overall quantity will have a dimension of electron volt squared. And if you basically use now the expression that I give you here and here, back in this quantity, you end up with a value which is about 119.5 electron volt squared. So this is the unit of Tesla in natural SI, in natural heaviside Lorentz units, 195 electron volts squared. There are also some other useful conversion quantities and identities to remember. So in astrophysics, we are often talking about energy in terms of ergs. So 1 erg, ERG, is equivalent to 10 to the power minus 7 joule. And if we convert joule also to natural units, this is identical to about 624 giga-electron volt. Then 1 Gauss is defined as 10 to the power minus 4 Tesla. So that means this is 1.95 times 10 to the power minus 2 electron volt squared from this identity. Then sometimes when we are talking about stars, we want to convert the mass of the stars to electron volt. For example, later we will talk about core collapse supernovae and how much gravitational binding energy we will have at our disposal from this collapse. In that case, it's useful to know the conversion between electron volt and kilogram. And 1 electron volt is equivalent to about 1.8 times 10 to the power minus 36 kilograms. And when we're talking about distant sources in our galaxy and across the universe, the typical distance scale that is used to measure distances is parsec. So 1 parsec is equivalent to about 3.26 light years. So the distance light travels within 1 year times 3.26. And in natural units, this has, in SI units, this has a value of about 3.09 times 10 to the power 16 meters. Okay, so I hope these are basically all the identities which are going to be important in the following. And so you can use these 2 slides as a reference also for exercises to convert between different unit systems. Are there any questions at the moment? Okay, shall we actually have a short break right now? There's one question. Yes, so there was a question, could you also have the slides? Yes, of course. So the advantage of using this pad here is that after this lecture, I can actually convert this to a PDF. And I'm not sure how I'm able to distribute this, but for example, I can distribute this via Slack, or I can send this to the organizers, and then you will have this information for the exercises then tomorrow. How do I get rid of this window now? Okay, so if there's no need for a break right now, I'm going to continue. So these were the preliminaries. So we have now to study cosmic ray charged particle transport in magnetic fields. Let me bring up a new slide here. So in the following, we will look for particles in the under the influence of magnetic fields. So the Lorentz force that I've already introduced here is given by this expression. I hope you can read this. So my vector notation is that I try to draw a little arrow on top of quantities, but I realize that my arrows are not really looking like arrows. So if you cannot read my handwriting, please interrupt me at any time, and then I will explain. Also, if you spot any errors while I'm writing, I'm very grateful if you just interrupt me and point this out, then everyone is on the same page, okay? So in the following, we are going to deal with cosmic ray transport in astrophysical plasmas. These plasmas are typically ionized. That means they cannot support electric fields. So whenever you have electric fields that are building up in a plasma, they are automatically short circuits by the charged particles in the plasma. So that means the Lorentz force that we are going to deal with in the following reduces basically to the interaction with magnetic fields. So we will assume in the following that electric fields can be neglected in our calculation. Of course, this is not entirely true from time variations of magnetic fields, which are very frequent in magnetohydrodynamical simulations, you will also generate electric fields. But for simplicity, I will ignore this effect in the following. So we are only dealing with particle motion in time constant magnetic fields. So magnetic fields which are not necessarily constant in space, but they are constant in time. So the motion of a charged particle is of course governed by Newton's law. And so this is the time derivative of the free momentum equals force. And so this is now given as Q. And the velocity vector beta, that is related to momentum in the following way. So m gamma times beta is equal to momentum in natural units. And in natural units, we also have that m times gamma is equal to P0. So this is the energy of the charged particles. So that means we can write the velocity vector simply as P divided by P0 across the magnetic field. And so this equation can be rearranged a little bit. We can write P dot is equal to P. So this is the free momentum again, bringing this in front of the equation. And then we combine the rest of this equation to Q, the charge, times the magnetic field divided by gamma n, which is basically the expression in natural units for the energy of the particle. So this quantity here, this is what we are going to call capital omega vector. So this is basically the rotation, the quantity that defines the rotation of the velocity vector, the free momentum of the particle in the external magnetic field. So the rotation vector omega has a frequency, and the frequency is the so-called Larmor frequency. It's basically the absolute value of this vector omega. So this will be 2 pi divided by capital T. So this is the angular frequency, the time it takes to go once around the circle. And this is, of course, given by Q times the absolute value of the magnetic field strength divided by gamma m. And with this, we can also define the Larmor radius. So the particle is the cosmic ray with a momentum P is going to circle around the magnetic field direction. And for positively charged particle, you can use the right-hand rule to figure out that for positively charged particles and magnetic fields, which are pointing in our direction, the force is going to, the Lorentz force is going to point in this direction. So the particle is going around this circle. So the radius of the circle is now the so-called Larmor radius, RL. So this is this radius here. And the Larmor radius is defined by the circumference of this circle, 2 pi times RL. And this is given by the total time for the cosmic ray to go once around times the velocity, which is in natural units simply beta. So you can rearrange this to find an expression of the Larmor radius, which is beta over omega. And this can be written m gamma beta over q times 1 over the magnetic field strength B. And this quantity here in front is the same as the absolute value of the momentum divided by the charge times 1 over B. So this combination of the 3 momentum of the particle divided by the charge, this is a quantity which we call rigidity, which is denoted by a capital R. So you see that the interaction of cosmic rays with the background field, that is not primarily dependent on the energy. The true dependence comes from the rigidity. So the 3 momentum divided by the charge of the particle, for very energetic cosmic rays, the 3 momentum will have the same scale as the energy itself. So the velocity b will be close to the speed of light, which is equal to 1. So in that case, the rigidity is simply the total energy of the particle divided by its charge. And the energy in natural units is measured in terms of electron volt. So if you have electron volt divided by the charge, you end up with a quantity which is proportional to volt. So rigidity is measured in units of volts in the following. Are there any questions at this point?
Is the time derivative in the momentum proper time derivative?
Yes. Yes. So this is the total time derivative in the reference frame of the particle. Okay. Yeah, maybe let me, I think at some point we also want to have a break, right? Not sure if it's time yet, but let me continue maybe for one more slide, and then we will have a little break where you can also ask questions and make some coffee. In particular, I will make a coffee. So let me try bring up another page here. Sorry, what you cannot see right now is how I'm trying to work with my iPad. This is something that I have to get used to a little bit. So let me give you an example about the size of the Lama radius. So in the following, we are going to talk about cosmic rays with an energy of 10 to the power 15 electron volts. So this is 1 peta electron volt. And of course, at these energies, if we are looking for cosmic ray protons, then this is a very relativistic particle. So basically P0 becomes equal to the absolute value of the 3 momentum in natural units. And the proton has a charge Q, which is equal to E, the elementary charge. So we can now again try to exercise a little bit the conversion between natural units and SI units. So the Lama radius that I derived on the previous page was given by the energy, so 10 to the power 15 electron volts divided by E times the magnetic field. So for the magnetic field in the following, I will assume 10 to the power minus 6 Gauss. This is a typical magnetic field strength that you encounter when you look for cosmic ray propagation in our own galaxy. So the Milky Way is basically supported by a magnetic field that is of the order of micro Gauss, so 10 to the power minus 6 Gauss. And this is equivalent to 10 to the power minus 10 Tesla. Yeah, so we are using 10 to the power minus 10 Tesla. And in the previous exercise, we have already dealt with factors of E. So this simply becomes 4 pi alpha in our unit system. And the scale of Tesla that we derived on the previous slide was 119.5 electron volt squared. So we see that 1 electron volt is actually cancelled in this equation. And now if we want to convert this back to SI units, we simply have to multiply this by 1 factor of h bar c, because h bar c in natural units has h bar c in SI units has the dimension of length times energy. So electron volt times meter. So this allows us to convert this back to length scales. And yeah, to make a long story short here, this is going to be of the order of 3.3 times 10 to the power 16 meter. And this is round about 1.1 parsec. Yeah, so about 3.5 light years. So we can rewrite the Lama radius equation now in a compact way. The Lama radius is given by 1.1 parsec for rigidities of the order of 1 petavolt and magnetic field strength B of the order of 1 microgauss. Okay. Okay, good. Then I think we will have a break now for maybe 10 minutes for you to get a coffee. And if you have any questions, now is also a good time to ask. And you can always use the chat, the Zoom chat, to ask questions. And you can also sign up for Slack, and then we can even continue discussions after the lecture or in between the lectures via Slack. Okay?
Okay. Thank you, Markus.
Okay, good. Then let's have a short break, and I'll see you again at, let's say, 4:05. Okay?
By the way, for all the students, give a look to the news that was put on the chat by Nicolau Fornego, because there are links to some exercise sheet. Okay, thanks. See you later.
Charged particle motion in magnetic field by giving you the solution for the case that we have a static magnetic field. So if we assume that the magnetic field is constant in space, so B, which is in general a function of location, is simply B0. So a constant magnetic field. Then, of course, the Lorentz force, the motion of the particle, is given by P dot is equal to P vector omega 0. So omega 0 is now the constant magnetic field direction. And of course, the motion of the particle can be split between motion perpendicular and parallel to the magnetic field. And from this equation, the motion that is which is parallel to the magnetic field, so P parallel is not going to change in time, and instead the orthogonal component will go on a gyro rotation around the magnetic field. So the solution in this case can be written in the following way. So the component which is proportional to the magnetic field line, that is of course not going to change in time. And the component which is orthogonal, that can be written as the orthogonal component at time equal 0 times cosine of omega 0 times time. And then we have here a second contribution, which is scaling with the initial component of the free momentum orthogonal to the magnetic field line at time 0 cross omega 0 hat. So whenever I introduce hatted quantities like here, the hat means that this is a unit vector. So this is a unit vector in the direction of the magnetic field. And this scales with sine omega 0 times t. And of course, we can integrate this equation to then finally get the motion, the path of the particle, which is simply given by its original location plus b proportional over gamma m plus 1 over omega gamma m and then just the integration of the previous equation. This is a minus p omega 0 times cosine omega 0 t. And of course, you know very well that this is describing the path of helical motion around the magnetic field line. So if this here is B0 and the particle has initially this vector P, this momentum P, which has this perpendicular component initially and this parallel component, then the path of the particle will describe helical motion around the magnetic field axis. Okay, so these are some preliminaries. We also introduced here the size of the Lama radius. And let me give you two examples where you can see the relevance of the strength of magnetic field and how they influence the arrival of cosmic rays. So let's first talk about the geomagnetic field. So the geomagnetic field is approximately dipolar in the vicinity of the Earth. Over very large distances, it will be bended by the outflow from the sun, which is indicated here by this Bohr shock. And but in the vicinity of the magnetic field, we can treat the magnetic field as a dipolar contribution. And the size of the magnetic field is on the surface of the order of 0.2 to 0.5 Gauss. So if we go back to our previous slide, we see that now in this equation, we have to replace here the magnetic field by 1 Gauss. So this is 1 million microgauss. And if you look here now for the Lama radius of cosmic rays with a rigidity of the order of 100 gigavolt. So assuming rigidities of the order of 100 gigavolts and a magnetic field of the order of 1 Gauss, you see that the Lama radius is of the order of 0.5 times the radius of the Earth. So you see that for cosmic rays, which are at the lower end of the cosmic ray spectrum, the size of the Earth becomes comparable to the Lama radius itself. So that has some effect now as cosmic rays are streaming towards Earth and interacting with the dipolar magnetic field structures in the vicinity of the Earth. And we can single out two interesting effects. One effect is the so-called rigidity cutoff. So based on the models of the Earth magnetic field, you can try to investigate if a particle can actually reach the Earth's surface if it is at very low rigidity. And one way to study this is simply by backtracking these cosmic rays in magnetic field. This is what is shown here on the left-hand side as the so-called vertical geomagnetic cutoff rigidity. So what you're doing here is you reverse the path of cosmic rays and you assume that cosmic rays arrive vertically on the surface of the Earth. And then you try to find out if the interaction and the gyro motion of cosmic rays in the Earth magnetic field actually allows the cosmic ray to escape the magnetic field of the Earth. If that is the case, then it also means that cosmic rays which are arriving from distant sources in the galaxy will be able to reach Earth just by reversing the path. And from these exercises, you can find that there's actually a cutoff in the minimum rigidity that you can observe on ground. And this minimum rigidity depends on the Earth magnetic field model, and it also depends where you are on Earth. So close to the equatorial region, the dipolar field of the Earth is horizontal. And towards the pole, of course, the Earth magnetic field lines become more inclined. So that has different effects on the cutoff. And you observe that the cutoff for the arrival of cosmic rays is the highest the closer you get to the equator. So the typical strength of the cutoff, rigidity cutoff in the equator region is of the order of 10 gigavolt. So this is one effect. The other effect is the so-called east-west effect. So imagine now you are again at the equator, and so you're looking here at the North Pole. And so the Earth magnetic field is pointing in this direction from the point of view of the equator. And now you're looking for the difference of cosmic rays arriving from the east and arriving from the west. And what you can observe in this critical rigidity region of the order of tens and hundreds of gigavolt is that there is a deficit of cosmic rays observing from the east compared to cosmic rays observing from the west. And this has a simple reason. If you backtrack cosmic rays in the eastern direction, they would basically form a path in the dipole magnetic field which would intersect back with the Earth itself. So that means that this path does not exist. You cannot observe cosmic rays which are coming from that direction because it intersects the Earth. But you don't have this problem with cosmic rays which are coming from the west direction. Of course, they would also go on a circle if this was a constant magnetic field. But of course, the dipolar magnetic field has a reduced field strength the further you go away from the Earth. So the effect is much, much weaker for cosmic rays coming from the west. And this is actually a very interesting measurement to observe the difference between the cosmic rays observing from the east and the west, because this allows us to determine the charge of cosmic rays. So you can see here from the bending of these cosmic rays using the right-hand rule that the Lorentz force is acting in this direction if the charge of the cosmic rays coming from that direction is positive. And the same applies also for the other trajectory. So this is if cosmic rays were for some reason, sorry, did I say, yeah, positive charge, yeah. If cosmic rays were negatively charged, on the other hand, you would see the east-west effect in the opposite direction. Then you would have an overabundance of cosmic rays coming from the east. And we also made the estimate of the Lama radius for cosmic rays with an energy of peta electron volt. So for energies of the order of peta-electron-volt, these are high rigidity cosmic rays, which are close to the cosmic ray knee. So one of the features that I introduced at the beginning. And I also mentioned that the field strength of magnetic fields which are filling our Milky Way is of the order of 1 microgauss. So these two quantities that I introduced in the first example of the Lama radius were actually designed to illustrate that the Lama radius of cosmic rays in our galaxies is actually of the order of 1 parsec if we look for energies of the order of peta-electron-volt, but of course at lower energies the Lama radius becomes smaller and smaller. Now that has a very important consequence. So this is here a sketch of the Milky Way. Of course, we are not able to observe the Milky Way from this bird's eye view, but in the sketch you have our sun, which is located here at this point. And we have here the galactic center. And the distance between us and the galactic center is of the order of 7.5 kiloparsec. So this is 10 to the power 3 parsec. This is many orders of magnitude larger than the Lama radius in micro-Gauss magnetic field. So it would not be possible to observe distant galactic cosmic ray sources in terms of the arriving cosmic rays from that source, because the magnetic fields will send cosmic rays on a random walk throughout the Milky Way. And the arrival time of these cosmic rays due to this random walk in the Milky Way is millions of years after the cosmic ray source was actually active. Of course, in the Milky Way, we are not just dealing with regular magnetic field components that have a well-defined orientation. In the magnetic field, what will become very important is the random component of the magnetic field strength. And if this is a very strong component, then this will actually lead to the effect of diffusion. Okay, so are there any questions at the moment? So it's very important and useful for me if you ask questions, because I also have to try to figure out if what I'm telling you is too basic or is too advanced. Yeah, so the fact that you are not asking questions is probably telling me that this is too basic what I'm telling you right now. So, but don't worry, it's going to become complicated in a minute. Okay, so then let me continue now with transport equations of cosmic rays. Of course, in cosmic ray physics, when we are looking for the arrival direction of cosmic rays, we are not so much interested in individual cosmic rays. We are interested in the entire ensemble of cosmic rays. And so instead of dealing with individual particles, we are dealing with something which we call phase space density. So let me introduce to you or remind you of the concept of the phase space density. So phase space density, or PSD, is defined in the following way. So we're looking for the number of particles which are located at time t, point r, and velocity p in a small volume that spans dr dp. So this is the so-called phase space volume. And this is multiplied now with a quantity f t r p. And this is called the phase space density. So knowing the phase space density means that I know the number of particles which are contained in a infinitesimal phase space volume. So this is something, a quantity which is indirectly related to cosmic ray observation. And this makes it very useful to study this quantity to relate it to our observations. And for that, in order to see this, we can first rewrite the cosmic ray phase space volume. So rewrite the phase space volume in the following way. So we have dr vector, dp vector, and we can rewrite this as velocity times infinitesimal time interval. So this basically gives me one dimension of the space volume in the direction of the motion of a cosmic ray particle. And then I multiply this by the surface area orthogonal to the motion of the particle. And I call this dA perp. So this is basically another expression of dr. And for the second part, I can write this as d omega p squared dp. So this is now going to be our phase space volume element for the 3 vector. So this is equivalent to dp. So now I can use the definition of another quantity, which is called the spectral intensity. So the spectral intensity is written as F, depending on time, location, energy, and steradian, so the arrival direction of the flux of the spectrum. And this is given by the number of particles per unit interval in time, the omega steradian, the surface orthogonal to the direction of observation, and dE, the energy. And if you compare this quantity now with our definition of the phase space density using this expression here of the phase space volume, you observe that this quantity is related to the phase space volume in the following way. You can write this as beta times p squared, and then you have the derivative dp over dE, and then you multiply this by the phase space density that we defined before. And now this quantity here, dp over dE, that is the same as the energy divided by the size of the free momentum. And this is then simply given as 1 over the velocity, 1 over beta. Yeah. So you see that this quantity is actually now canceling the initial factor of the beta. So you see that the final expression is simply p squared FTRP. So the phase space density is in other words related to the spectral intensity of the flux of cosmic rays arriving at a certain direction, at a certain energy. And what we are often using when we are talking about cosmic rays is the so-called spectral density. And the spectral density is defined with this notation here, a small n, TR E for energy. And this is defined as 1 over the velocity. And then you have here the integral over the steradian. And here you have now the spectral intensity. And this can be written in terms of the phase-space density again as p squared divided by beta times d omega f. And in the following discussion of the phase-space density, we will often look for a moment expansion of the phase-space density. So basically the expansion of the phase-space density in terms of spherical harmonics. And if we are looking for the first expansion parameter of the spherical harmonic expansion, the monopole, then this is something which is independent of direction. So if we call this monopole phi in the following, we can rewrite this as 4 pi p squared over beta. Oops, sorry, I'm interfering here with some buttons that appear on my screen. Let me try to move this. See, I can move this, very nice. Okay, so 4 pi p squared divided by beta. And then I have here the average, the angular average of the phase-space density, which I'm going to call phi in the following. That will depend on T, R, and P. Yeah. So the phase-space density is related to the spectral intensity, and the spectral intensity in turn is related to the spectral density. So all the information that we need to understand cosmic ray propagation is already encoded in the phase-space density. One additional thing which is useful to know about the phase-space density is a Lorentz invariant quantity. And so this is something that can be seen from the definition of the phase-space density. You can rewrite the phase-space density definition in the following way. You have dn is equal to dr times dp times the phase-space density. And now I can multiply dr here by a factor of energy, and I can divide dp by a factor of energy. So basically nothing has changed. But you can show that these two quantities individually are Lorentz invariant. So they are Lorentz scalars. And of course, the n here that appears on the left-hand side, this is just the number of particles. So this is also a Lorentz invariance quantity. So that means that the phase-space density itself is Lorentz invariant. Okay, are there any questions at this point?
So
yeah.
In the previous equation, what does phi mean?
Yeah, so what I was, I only mentioned this in Word. I was not, I should be more careful. So this quantity will be introduced later on in a couple of slides, yeah. But I can repeat this real quick here. So the definition of phi, T, what did I say here? TR and P. This is defined as the angular average of the phase-space density. And maybe I should write this in a somewhat different way. So this is basically averaging over the orientation of the 3 vector and taking the space-dense density at P times the orientation of the vector. So this is the definition of phi. Does this make this clear, Mesper?
Yeah, thanks.
It's maybe not so obvious right now why this is useful, but I hope this will be more obvious later. And maybe while we are at it, we can also introduce another quantity. So this is also called here the monopole. As I said, we are looking at a spherical, basically a spherical harmonic expansion of the phase space density. We can also define here the dipole. This is basically given by the same expression, but now we are weighting this with the orientation of the free momentum in the direction A. Yeah, so this is going to be the dipole component that we are going to use in the following. And of course, you can do this for arbitrarily high moment expansions, but these are the two moments that will be important in the following. Okay, so in the last 10 minutes or so, I think I'm a little bit behind, but okay, let's see. Let's start about the evolution of the phase space density. So cosmic rays are interacting with magnetic fields. And so the interaction of cosmic rays with magnetic fields that can be described as a Hamiltonian system. So a system that follows Hamiltonian dynamics. And in these type of systems, I can use the fact that the phase space density is constant in time. So this is the famous Liouville theorem. And this is probably one of the simplest equations that you can learn in physics. Liouville theorem basically says that F dot is equal to 0. So F dot here is the total time derivative of the phase space density. And basically it means that, so another way to express Liouville's theorem is if you follow a particle in the distribution that is described by the phase space distribution, then the phase space volume that the particle experiences along its trajectory is going to be constant in time. Yeah, so if you have a particle that follows this trajectory, and so at this point, so this is at time t0, location r0 and momentum p0. And so this the phase space density at this point in a small phase space box is going to be ft0. And if you look a little later, following the trajectory of this particle up to a time t1 with momentum t1, then the phase space density at this point is going to be the same as the original one. And of course, you can do this at any arbitrary point along the trajectory of the particle. So the phase space volume of a particle or a particle ensemble is going to be constant in time because the number of particles remain constant in time, and the phase space density remains constant in time because this is the result of Liouville's theorem. Now, Liouville's theorem is expressed in terms of the total time derivative. So since F, the space density, depends on location and momentum, I can expand this expression and write it as the partial derivative of the phase space density plus the partial derivative with respect to location. So RA, so A is going to be the index running from 1 to 3, so indicating the three spatial coordinates. And this is multiplied by the time derivative of the location itself, which is basically the velocity of the particle. So this is the second term, and the third term is going to be the time derivative of the momentum and the derivative of the phase space density with respect to momentum. So here I'm using Einstein convention. So whenever I have repeated indices, it is implied that I'm summing over these repeated indices. So this is a sum here over A, and here on, so this term you're summing over A from 1 to 3, and you're also summing over A here from 1 to 3 for the momenta. Now the velocity of the particle, that of course is simply given as the 3 momentum divided by the energy P0. And we can use Newton's law to express the time derivative of the momentum as the Lorentz force itself. This is Fa. Are there any questions?
Can you repeat the hypothesis of the Uv theorem, please?
Yes, so the Uv theorem is a very important statistical theorem. It says that the total time derivative of the phase space density is 0. So the phase space density is constant. And it means that when I follow a particle within the phase space density along its trajectory, then the phase space volume along the trajectory is not going to change. Yeah, or in other words, if I want to know the phase space density at a time t1, I simply have to know the phase space density of the particles at earlier times t0 along the trajectory, and that is going to be the same phase space density. So this is important for us because we are going to talk about cosmic rays. So we want to find out how the local phase space density of cosmic rays, which is related to the spectrum of cosmic rays that we observe, how this is related to phase space densities at distant sources, in particular, how this compares to the distribution of cosmic rays in our galaxy. So we basically want to find out how can we relate the locally observed cosmic ray density to the appearance of cosmic ray sources in the galaxy. This will be our ultimate goal.
Okay, thank you.
Yeah. Okay.
Excuse me, Markus, we have 5 minutes left.
5 minutes. Okay, so I will continue for 5 minutes and then I will stop. Okay.
Okay.
Yep. Okay. So now replacing these two quantities gives us now this expression here, PA over P0. And here we have FA times the momentum derivative of F equal to 0. And this expression is also known as Vlasov's equation. So this is going to be our basic equation when we are looking for cosmic ray motion in magnetic fields. Now, in the following, we will consider the case that cosmic rays are not only interacting with regular magnetic fields. So we are assuming that the magnetic field at any location R is not only a regular component, which is independent on location, but it will also have a random component that we are going to call delta B in the following. And this random component is going to depend on location. So if we are now looking for cosmic ray motion in magnetic fields, what we are interested in is not so much the motion of cosmic rays in one particular magnetic field configuration. We would rather like to know what the average contribution of magnetic field configurations are. So instead of looking for the solution of the phase space density of one particular magnetic field, including also turbulent components that are called delta B in the following, I'm interested in the ensemble average. And ensemble here means that we are looking for various different magnetic field configurations that cosmic rays can encounter as they stream through the galaxy. So the additional component that I have here, this is going to be the turbulent component. And this here is the regular component, constant in time. And I will assume in the following that the ensemble average, so averaging over all possible magnetic field configurations, is going to be identical to the random magnetic field. So that means that the ensemble average of the turbulence is going to be equal to 0. And this also means in term now, if I'm looking at the definition of the Lorentz force, so this was given as the charge and the momentum of the particle across the magnetic field can also be written as in terms of the Levi-Civita symbol ABC, beta B, BC, and epsilon ABC. This is going to be 1 if ABC are in order. And also cyclic perturbation, it's going to be -1 if I have the reversed order. Cyclic permutation, and it's going to be equal to 0 otherwise. I hope you can read this actually. Okay, so this is the Lorentz force that I'm going to use. And because the Lorentz force is proportional to the magnetic field strength, it basically means that I can also decompose the Lorentz force here into a constant force, which is depending only on the regular magnetic field, and a component which only depends on the turbulent component. And the contribution to the Lorentz force, depending on the turbulent magnetic field component, this is what I call delta FA in the following. So now you can, maybe in the last minute that I have, I can look at the ensemble averaged Vlasov equation. And the ensemble average Vlasov equation is going to look as follows. I have here the partial time derivative of the ensemble average of F. Then I have the spatial derivative of the ensemble average. And I have the average component of the Lorentz force, which only depends on the regular magnetic field. And this multiplies here again the ensemble average. But then I also have a cross term, and this cross term is basically depending on the fluctuation of the ensemble average. So I can write F in terms of the ensemble average plus a correction delta F. And so the right-hand side of the ensemble average Vlasov equation is not going to be 0, as in the case of the original Vlasov equation, but instead I'm going to have a term which is written minus the ensemble average of delta FA, and then I have here the derivative with respect to the momentum on the correction delta F. And this term that appears here now on the right-hand side, this will be abbreviated in the following as this contribution, which is also called the collision term. So this is an effective collision term, which is introduced by magnetic field irregularities as cosmic rays are streaming, for example, through our galaxy. And I think this is a good point to stop now. And we will continue with the Vlasov equation then tomorrow morning. Okay, are there any last questions?